perhaps the most interesting of all laws of thermodynamics because it excites the most discussions and may seem counterintuitive. That's the second law. It deals with the behavior of entropy. The second law says that whatever process a system undergoes, whatever happens inside an isolated system, it can never lead to a decrease of entropy. The entropy may possibly stay the same or it may increase, but the entropy can never decrease. So the statement is that the total entropy of an isolated system can never decrease. Now, the isolated system may in turn be composed of several subsystems. Yeah? So you may have several subsystems that are in contact with each other, possibly exchange heat, particles, and so on. But together, they constitute an isolated system. And whatever happens now inside this big isolated system can never lead to a decrease of total entropy. And this reflects, as you certainly all know, this reflects the fundamental irreversibility of macroscopic processes. As I said, there are lots of discussions and arguments even today about the meaning and the proper derivation of the second law of thermodynamics. Let me give you an argument that I personally found the most convincing, one of the most convincing arguments that I've seen so far, and at the same time a rather simple argument. It's an argument that goes back to Edwin Jaynes. He first published that in the late 50s or early 60s, if I'm not mistaken. He invoked the argument that macroscopic experiments must be reproducible. And let me try to explain what that means and how that implies the second law. Let me state the basic idea and then fill this idea with mathematics. The idea is that when you're given certain data, and on the basis of these data you make a prediction, then the prediction cannot possibly contain more information than the data on which you base your prediction. These are not his words, but this is how I understand his basic idea, that a prediction cannot contain more information than the data on which it is based. This implies that the information content can only decrease. It can stay equal at most or decrease, but it cannot increase. We talked about the close connection between information and entropy. We said entropy is a measure for our ignorance about the microstate. It's a measure for the lack of information about the microstate. So when we say information cannot increase, a prediction cannot contain more information than the data on which it is based, so the information can only be less or equal but cannot be more, then this means that the associated entropy, so the lack of information, the ignorance, can only be more or at most equal, but it cannot decrease. That's the basic idea. Let's try to cast this into a mathematical form. When we perform an experiment on a macroscopic system, what do? Initially, we prepare the system. So we prepare an initial macrostate. Preparing a macrostate means fixing the values of the observables that constitute our macroscopic data. So preparing an initial macrostate means fixing macroscopic data which are expectation values of some set of macroscopic observables AI. And then the initial macrostate must have the form rho naught. Let me give it a prime, meaning a macrostate. As we learned, it has this generalized Gibbs form, e to the minus sum over I, Lagrange parameter lambda I, AI. So preparing the macrostate, the initial macrostate, means fixing an initial macrostate of this Gibbs form. Then the system somehow evolves, something happens, and at the end we do a measurement. And again, what we measure are only macroscopic properties of the system. So at the end, we measure again macroscopic data. And the observables that we might measure at the end might not be the same, or need not necessarily be the same as the ones that we prepared initially. So to be general, we can say that we measure macroscopic data which may be some different set of observables B, J. And they correspond to a final macrostate. Let me call it rho F for final, prime for macroscopic, which has the form, again the generalized Gibbs form, e to the minus sum over j, and let me introduce a new Lagrange parameter because we have different observables, nu j, bj. So this is what we do in the lab when we work with a macroscopic system. We prepare initially some macroscopic data pertaining to observables AI, and then we let the system evolve, and at the end of the experiment we measure again macroscopic data. This may be some different set of macroscopic observables Bj, and initially the macroscopic data that we prepared corresponds to this macrostate rho naught primed, and the macroscopic data that we measure at the end corresponds to a final macrostate rho F primed. The experiment is reproducible if, on the basis of our initial preparation, we can predict the final measurement results. So if we repeat the experiment, we do the same preparation of the macroscopic state, we'll get at the end the same result. If this is the case, then the experiment is reproducible. So it is possible to predict the final macrostate. So this is what we mean by macroscopic reproducibility. Let me write it down once again, that the initial macrostate, let me abbreviate it like this, the initial macrostate or initial macroscopic data uniquely determines the final macrostate. Now this holds regardless of any prior history of the system, whatever happened before we prepared the macroscopic data, the AIs, so regardless of any prior history of the system, and also regardless of the initial microstate of the system that the system is in. So there are, of course, many different microstates that are compatible with the initial macroscopic data that give the same values for the macroscopic observables AI. But regardless of which of these microstates the system is in, as long as we are given this macroscopic data initially, we can predict the outcome and the final macroscopic data. So regardless of the initial microstate, as long as the microstate is compatible with our macroscopic data. Above this horizontal line, this is what happens on the macroscopic level where we perform our experiment. Above this, there is a microscopic level. What happens exactly on this microscopic level is not known to us because we control the system and we measure the system only on the macroscopic experimental level. But in theory, of course, there's this microscopic level. Microscopically, we have some initial microstate, which are called rho naught, which is unknown to us. On the microscopic level, when we talk about an isolated system, states evolve according to unitary evolution. So on the microscopic level, whatever this initial microstate is, will evolve with a unitary time evolution operator U. This is because we have here an isolated system, and therefore we have unitary evolution. This will then lead to a final microstate, rho f. That's the final microstate. And the final microstate is nothing but the initial microstate after unitary evolution. Let's look at what happens with the entropy in this scheme. The initial microstate has some entropy S of rho naught. The final microstate has an entropy S of rho f. But since rho f is related to rho naught by unitary evolution, and entropy is invariant under unitary evolution, the entropy of the final microstate equals the entropy of the initial microstate. When you look at how the final microstate and the final macrostate are related, they must of course be compatible in the sense that they give rise to the same expectation values for your relevant observables, for the B's. So the final microstate must be compatible with the macroscopic data that you measure at the end of your experiment. So the micro and the macrostate at the end, they must give the same expectation values, they must give rise to the same macroscopic data. Now the macrostate is the one that, given the macroscopic data, maximizes the entropy. So of all states that give rise to the same macroscopic data, so the values for the Bj, the macrostate in this Gibbs form is the one with the highest entropy. So in particular, the entropy of the final macrostate must be larger or at most equal to the entropy of the final microstate. Because in the process of going from the microstate to the macrostate, you lose information, all information that does not relate to the macroscopic data. So perhaps a better way of writing this here along this arrow is that going from micro to macro, you keep information about the macroscopic data, so the values of the Bj only. And in doing that, you throw away all other information and you increase, in the process, you increase the entropy. So what we've seen so far is that the entropy of the final macrostate is greater or equal the entropy of the final microstate, and this in turn is equal to the entropy of the initial microstate. There's one piece missing here in this scheme, and we said that we have this macroscopic reproducibility regardless of which initial microstate we choose. So it doesn't matter, as long as we prepare the initial macrostate on the basis of the AIs, it doesn't matter what the underlying microstate is. So if all we know initially, because we prepared it, is the initial macrostate, then as for the microstate, we can pick any microstate that is compatible with our initial macrostate. In particular, we can also choose rho naught to be equal to rho naught primed. We are free to do that. So this scheme that I drew holds generally, and we have this reproducibility regardless of the microstate, that's the initial microstate that's underlying the initial macrostate, as long as it's compatible, as long as it gives the same values for the AI. Now, a special choice for the microstate is to say it's simply equal to the macrostate. So we can choose for the rho naught, we can make any choice that gives the same expectation values as the rho naught prime for the AIs. In particular, we can choose the rho naught to be equal to the rho naught primed. In this case, the entropy of the initial macrostate equals the entropy of the initial microstate, which in turn equals the entropy of the final microstate, which in turn is less or equal the entropy of the final macrostate. So when you look at the extreme ends of this chain of equalities and inequalities, you see that the entropy of the initial macrostate is less or equal the entropy of the final macrostate. Or the other way around, the entropy of the final macrostate is always larger, greater, or equal the entropy of the initial macrostate. So on this macroscopic level, the entropy can only increase or stay equal, but it cannot possibly decrease. And it's a consequence of this requirement that experiments on the macroscopic level are reproducible. That as long as you prepare some initial macroscopic data, no matter what the prior history of the system is, no matter what the precise underlying microstate is, as long as you prepare these initial macroscopic data, you will have, at the end of the experiment, you will have always the same final macroscopic data. As long as this is the case, then you have this inequality for the entropies. Now, just a few final remarks. The fact that the second law of thermodynamics is so closely linked to the reproducibility of macroscopic experiments leads to an inverse statement that it is actually possible, and it does happen, that you see temporary violations of the second law. But such violations of the second law are never reproducible. They are random fluctuations, and they are not reproducible. Or when people claim, and sometimes this happened in the past, that people claimed to have observed violations of the second law, in fact in a reproducible fashion. And then when you look more closely, then you find that the macroscopic data that purportedly characterized the initial macrostate was in fact not complete. That actually there was a peculiar prior history of the system or prior preparation of the system that involved the preparation of additional macroscopic degrees of freedom or macroscopic observables, and that therefore the set of observables that people claimed was characterizing the initial macrostate was actually not complete, that people omitted macroscopic data, and that as soon as you include these missing macroscopic data, then the validity of the second law was restored. So you cannot get around the second law as long as you include all relevant macroscopic data. And if someone sees a violation of a second law, then it's always temporary and it's always a random fluctuation and it's never reproducible. I spent quite some time on the second law because it's so fundamental, and I hope that I could convey this basic idea that the second law is intimately linked to this reproducibility of experiments on the macroscopic level. I'd like to show you a little illustration, a pictorial illustration of the second law, of the argument that I had presented on the previous page. It's a conceptual illustration, so you have to take it with a pinch of salt. Imagine a state space, and for simplicity, let's use a classical picture. I don't know how to draw quantum state space so easily. So think of classical state space, which is phase space. Of course, when you have a macroscopic system, it has a huge dimension, which is impossible to draw. So this will be a two-dimensional state space. And in there you have microstates, schematically represented by these dots. So you have microstates. Now let's say you are given some initial macroscopic data, either in the form of sharp constraints or in the form of expectation values, and a certain set of microstates is compatible with these constraints. And let me indicate with this set the set of all microstates compatible with your initial macroscopic data. And the microstates inside this set represent all microstates that are compatible with this initial macroscopic data. In time, these microstates evolve quantum mechanically by unitary transformation. Classically, you have a Hamiltonian flow in phase space. And after some time t, this initial set of compatible microstates will have evolved in another set, which, let's say, has this shape. And in there are the final microstates that have been mapped from the initial microstates by time evolution. So Hamiltonian classically or unitary quantum mechanically. You've probably heard in your classical mechanics course that about the so-called Liouville theorem, which states that in classical phase space, volume is preserved under Hamiltonian evolution. So this final blue set that I indicated has the same volume in phase space as the initial blue set. Now we said that On the basis of the initial macroscopic data, we can predict the final macroscopic data. This implies that all the microstates after time evolution must be compatible with the final macroscopic data. So let me indicate by yet another set all microstates that are compatible with the final macroscopic data. So we said the initial macroscopic data that may relate, for example, to certain observables AI. After the end of the macroscopic experiment, we measure macroscopic data that may relate to a different set of observables Bj, and there is a certain set of microstates that is compatible with the final macroscopic data. And this set is indicated here in purple. Now, when we say that the initial macroscopic data uniquely determine the final macroscopic data, so the experiment is reproducible. Whenever you prepare the initial macroscopic data, you will always get the same final macroscopic data. It's reproducible. The final macroscopic data are predictable. Then this implies that the evolved blue set must lie inside the purple set. Only this ensures that regardless of the specific microstate that you had at the beginning, the final microstate is always compatible with the final macroscopic data that you observe. Right? So reproducibility implies that this blue set must be contained in the purple set. Otherwise, the macroscopic experiment would not be reproducible. Now, it's obvious then that the purple set must have a larger volume than the blue set. Entropy, when you think microcanonically, entropy is the log of the number of compatible microstates. The purple set must contain more, or at least as many microstates as the blue set, and therefore the entropy associated with the purple set must be greater or equal the entropy associated with the blue set. And this is nothing but the second law, that you say the entropy associated with the final macroscopic data, so with the final macrostate, that's the entropy associated with this purple set, cannot be smaller, it must be greater or equal than the entropy associated with the blue set, which is the entropy of the initial macrostate. And so this is a symbolic representation of the more mathematical argument that I showed you on the previous page.